Welcome friends. We are discussing network theory. So in the last session we have discussed the Laplace transform and its definition, its few important properties, and Laplace transform applied to few standard signals. Even before that we have also solved, or we have also studied the transient response behavior of series RL circuit, series RC circuit, series RL circuit. Now while we have done that, we have used time domain approach, that is differential equation approach. Now in this module 9 we shall see the application of Laplace transform technique to solve transient response in series RL circuit, series RC circuit, series RL circuit. Now this is an alternative approach by which you can solve transient response of electrical network. Now first of all, let us try to understand why should we adopt, or why should we at all require to have this technique. So what is the problem with the time domain approach? So let us try to first understand that. Let us try to understand by simple example. Let us say we want to evaluate 2 into 3. So without any delay, anyone can say 2 into 3 is equal to 6. Okay, 2 into 3 equal to 6. Anyone can tell. Normal human intelligence can able to answer this sum. However, if I place this problem like this, 2.749 into 3.125 is equal to how much, then normal human intelligence cannot solve this problem. Normal human intelligence cannot solve this problem. We require calculator. We require calculator. Okay. So if the problem is very straightforward, it's a very simple example, right, through which we can understand, or we try to understand what is the need, why Laplace transform is needed. Okay, so please try to understand this analogy. If this problem is very straightforward, 2 into 3, so normally we can say this is equal to 6. However, if the problem is something like that, 2.749 into 3.125 or something like that, so we cannot answer this question because it is beyond of our capability, human capability, right? So we require calculator. Now what calculator actually does, calculator will first evaluate the log of these two numbers. Okay, it will evaluate log of 2.749 and log of 3.125. okay, from there they will add. Let us say this is x, this is y, so it will add x plus y. Okay, it will add x plus y, because you know if it is a multiplication, then in the log rule it should be added. From there again you should take anti-log. Again you should take anti-log. So to get the answer, anti-log of x plus y, which is your answer, that is your answer, right? So calculator does exactly these 3 steps. First it calculates log of those two numbers or n number of numbers. Then it should add or subtract depending on the problem you have given instruction, and at the final step the calculator does what? It evaluates anti-log of that product or of that result, x plus y or x minus y or whatever. So this entire thing is inbuilt inside that calculator. Okay, so we can understand that if the problem is very straightforward, then we can normally intelligence, normal human intelligence can tell. Okay. However, if the problem is little bit complex, then we require the help of calculator. Now please try to understand this. If we say, or if we have a differential equation in this fashion, dy dt plus 2y is equal to 6. dy dt plus 2y is equal to 6. Now for this we can directly write its answer. We can directly write its answer. Y is equal to k into e to the power minus 3t or something like that. Okay, it's something like that. K should be evaluated from the initial condition. So it's just like 2 into 3. So it's a very straightforward differential equation. Straightforward differential equation. Straightforward differential equation we can directly solve. However, if the differential equation is like that, d cube y dt2 minus 7.3 d2y dt2 plus 5 dy dt minus y is equal to some value or some function of t, et. So you know you require some help. You must require some help from outside. Okay, your normal differential equation approach will not work here. Even though it works, it will take large amount of time. So we do not have so much of time to solve that. So what it does actually, so that is the role of the Laplace transform here. That is the role of Laplace transform here. It first converts time domain into frequency domain. Okay, then it will do some algebraic manipulation. Algebraic manipulation. After that, we should evaluate inverse Laplace transform. We should evaluate inverse Laplace transform to get my answer. So here is the utility of the Laplace transform. So if you compare, if you do a comparative study, you see the differential equation approach or time domain approach or classical approach is very good when the problem is very simple and straightforward. It's simple and straightforward, right? They will work very good. You can directly write the answer. However, if the problem is of higher order, or if the problem is of, for a complex network, if you want to solve the transient response, then time domain analysis or time domain approach will take large amount to solve, large time to solve. So we shift Laplace transform for complex problem and complex network. So it will reduce our time, it will reduce our effort considerably. So Laplace transform technique works very well for a complex network problem. So this is the a comparative analysis between time domain approach and Laplace transform approach. Okay, so just you can see that if anything it needs to be multiplied, right? If anything needs to be multiplied x into y, first your calculator will calculate log. So let us say that is be p and q. Then that calculator will do some algebraic manipulation to get a new number r. Then from that r, if it takes anti-log, then you will get the answer. You will get the answer. And now this path will work well. This path will work well if the problem is a very straightforward problem. However, this enlarged path will work well for a complex problem, right? just like this, if we have a very ordinary differential equation, straightforward differential equation, the straight path, which is time domain approach or classical approach, will work very well. However, if the problem is too large, too complex to handle, then we must apply the Laplace transform. So from the time domain, it first converts it to the frequency domain, which is called Fs. Now on that Fs, you must impose some initial condition. What is initial condition? That is inductor current I0 plus and capacitor voltage V0 plus. These are called initial conditions, inductor current and capacitance voltage. So from that Fs, we need to do some algebraic manipulation seen in case of problems. Then with the modified Fs, you need to take inverse Laplace transform to get the solution. So if the problem is too large or too complex to handle, then you should follow this Laplace transform approach technique. It will solve, or it will save your time, effort very much. Okay. So this is a comparative analysis. Why should we use Laplace transform technique? That means why not always to use time domain approach? Because it is not actually very good, or it will not work well. It will take large time to solve a problem with a higher order. Okay. So Laplace transform technique is a better technique to solve these issues. Now some transformation we have seen already previously, but just for a recap, let us do again. Suppose we have a DC voltage source. V. So voltage source, DC voltage source, since it is a constant value, so it will be acting as a step input. So its Laplace transform is V by S. Its Laplace transform will be V by S. Similarly, if a constant value current source, again it is a step input, so its Laplace transform will be I by S. Now when the voltage source is a time dependent, Vt, okay, then its Laplace transform must be Vs. That means time dependent voltage, so that means it is a function of time, so its Laplace transform will be function of S, Vs. Similarly, current IT, that means the time dependent current IT, if you transfer them into the frequency domain or Laplace domain, its Laplace transform will be Is. That is a function of S. Now let us moving on to our next thing, that is what will be the voltage across the inductor. Very important. What is the voltage across the inductor? Suppose suppose if this is an inductor and if some current is flowing IT through that inductor, so what will be the voltage across the inductor? VLT. So it is L into di dt. Okay. So if we convert the Laplace transform, then it will be VLS, that will be, now you follow the derivative rule, Laplace transform of the derivative rule. If you remember, it is S into Is minus I0 plus. Okay. So then it should be is equal to SL into Is minus Li0 plus, right? So this is a very important equation, that is inductor voltage across the voltage across the inductor in Laplace domain is nothing but current Is that multiply into SL. So that SL must be inductive reactance. Then SL must be inductive reactance. With that, we have a constant value L into I0 plus. So this must be a constant value because L is constant, I0 plus, which is initial condition, that is also constant, so it will give you a constant value voltage. So if you represent this equation as per circuit diagram, then figure 2b will be representing this equation. So where this inductor voltage, the total voltage across that inductor will be VLS, where inductor is replaced by SL in the Laplace domain, inductor is replaced by SL in the Laplace domain, so that current is flowing IS. So IS into SL, okay, IS into SL, that along with this must be acting as a voltage source, that must be acting as a constant value voltage source with magnitude L into I0 plus, because it is a voltage equation. It is a voltage equation. So this must be some constant value voltage source. So this is the application of, directly you can understand, it is a application of derivative rule, okay, which you have, or which we have discussed in the module number 7. Sorry, module number 8, while discussing the properties of the Laplace transform. Okay, so when inductor is encountered, then its equivalent representation in the Laplace domain will be SL. It will be represented by a SL. That is a very interesting or important observation you should make. Now what will be the current flowing through the capacitor? Okay, so similarly again, when some current is flowing through the capacitor, then IC, that is the current flowing through the capacitor, IC or IT, whatever it may be, that must be C dV dt. That must be C into dV dt. It is well known equation. So with that, if you convert it in the Laplace domain, ICT will become ICS, ICT will become ICS. Then C, if it commons, now dV dt, it will become S into Vs minus V0 plus. Similarly, or if you simplify, ICS, that will be equal to Vs. Now you see that CS can be written as 1 by SC. CS, it can be written as 1 by SC minus C V0 plus. So now this is a current equation where this ICS is the current flowing through the capacitor. So this current should be flowing through the capacitor. Now we can write ICS plus C into V0 plus, that is equal to Vs over 1 by CS. So actually two currents, this is one current and this is also another current, because this is a constant current, this is a current equation, so this must be a current, constant value current, constant value current. Okay, so these two currents will add up and make this current. Okay, so what is this? So you see the input current IS is entering in this way, and this constant value current C V0 plus, which is entirely dependent on the initial condition, it is entering in this fashion. So when these two currents are meeting at this node, one current must leave, so it must be, so what is that current? So voltage appearing voltage appearing across that capacitor, which is Vs, divided by capacitive reactance, which is 1 by Cs. Okay, which is 1 by Cs. So it means, quite important observation you must make. So when a capacitor is there in the time domain, it must be represented as 1 by SC in the frequency domain. It is capacitive reactance, XC, capacitive reactance. So with this, it is very important to understand that when an inductor is present, then it must be represented by SL in the Laplace domain, and when a capacitor is present, it must be represented by 1 by SC in the Laplace domain or frequency domain. So we have understood that why Laplace transform is better over time domain analysis or the time domain approach, which is differential equation approach. Then we have seen two important properties of L and C. When L is represented in time domain, its equivalent reactance representation in frequency domain is represented by SL. And in case of a capacitor, its equivalent capacitive reactance is represented by 1 by SC. So with this, I am ending this part here. From the next session, we shall see transient response of RL circuit, RC circuit, RLC circuit using Laplace domain analysis. Thank you.